So I think we can, if you can take your seats, we can start this session. This is the session on human and human networks and real networks enabled with grids. So we will try to address this topic with three presentations. The first presentation showing two projects, so two grid projects which are actually creating the human network, and the last two presentations on some software which can enable this grid infrastructure and creating this human network, human grids. So the first speaker is Federico Ruggeri from INFN, and they will talk about the UMed grid and the U-China grid project. So please, Federico.
Hello? Yeah. Okay. So, thank you. I have to first thank all the organizers for inviting me to this Terrena conference and to give you this talk on these two EU-funded projects which just started. And I will try to show you which are the commonalities and differences between them. So, first of all, the commonalities of those two projects is that they aim to extend as much as possible outside Europe the grid technology and to share with other countries the successful best practices that have been experimented in large infrastructures like EGE. It's certainly true that although Europe and other most advanced countries has invested a lot of money in these last years to make grid technology, grid infrastructure grow, there is still a lot of countries which are not yet involved in grids, and it's, I think, a good way of pushing their research community to start to think to grid as a useful system to make their research activities grow. And we think that the grid infrastructures has two ways in which can essentially give benefits to those communities. One is fostering essentially the formation of international groups and applications, and the other one is to enable or discover new world-class collaborative solution. So why Mediterranean in China? Well, Mediterranean area is essentially in the neighborhood of Europe, and so it's quite natural to try to extend the research area, which is one of the main goals of European program, to those countries and try to collaborate with them to grow this research area. So that's why we started this UMed Grid project, which as a title has empowering e-science across the Mediterranean. And on the other hand, China is one of the biggest economies nowadays. It's very fast growing, and essentially they have already started some great projects, and we got in contact with one of them, CN Grid, which is essentially for science grid. And we think it's a good idea to establish with them good relationships and try to interoperate with them. So find common applications, common ways of distributing the scientific application between Europe and China. Hello? Yeah. Hello? Yes. Okay, so let's start with UMedGrid. A few numbers. It is a new funded project which is called a specific support action, for those who know what this means. And it officially started on the 1st of January and has 24 months duration. We have 14 partners, 9 for Europe member states and 5 for non-member states. And the Europe contribution is 1.6 and something million euros. The main objectives were to try to essentially foster the creation of national grid initiatives in Mediterranean countries and try to coordinate them in a new grid infrastructure which can be linked to the EGE European infrastructure and try to collaborate with the EGE for having common policies and common software if possible, and common application as well. So the reference grid infrastructure is essentially EGE, but we also intend to make use of the existing networking infrastructure, which are essentially the GEANT in Europe and the European funded project UMedConnect. The participants are, as I told you, 14. Most almost all of them are European country or Mediterranean countries, which are on the Mediterranean. There is only one exception, as you can see, CERN, which is not precisely on the Mediterranean, but I mean, it's an obvious choice as a technological partner because they are leading the EGE project. We have also a good list of third parties in the area, with even more countries like Jordan and Palestine and Israel. So this is the split into work packages of the work program. We will essentially do in a WP2 the capture and analysis of requirements in the area, and with this information we will be able to pinpoint specific applications in the area which are of interest for those countries and which will be one of the regional applications that we want to deploy on this pilot infrastructure. WP3 will be essentially dedicated to support the creation of these pilot national grid infrastructures and services in the countries. And WP4 will support the usage of applications on this pilot infrastructure. We will start with the already supported EGE applications, which are obviously much more easy to deploy, but also basing ourselves on the results of WP2 survey, we will find some regional applications which are of interest for the region, and we will deploy them on the grid. And we will also discover new applications, also making use of the WP2 survey, and we will try also to address those on the grid. And obviously, finally, last but not least, we need to train people and to disseminate the advanced knowledge related to grid technology. So this is the infrastructure we are planning to build. As you see, almost all the Mediterranean countries are in the project, and they have already started their work, as we can see. And this is the EUMEDConnect network where we are basing on. We are essentially using this infrastructure, which, as you can see, is sufficiently good to start grid services, and which will allow us to implement good grid connectivity among those countries. So the achievements in the first 4 months are essentially that we have correctly started our work. We did a very successful kickoff meeting in Malta, where essentially all the Mediterranean partners were present. This was already a good achievement from the political point of view. We had around a table all the countries in the Mediterranean area, and nowadays this can be considered already a good achievement. We had already a first tutorial in Athens, well attended by the countries, and we have also started a preliminary pilot infrastructure with 6 sites, and the others will come in the next months. So the community requirement survey was started as well, and the questionnaire was finalized in March, and it was sent around and was available on the web. And we had already 96 answers, and the results of those questionnaire are under analysis and will be the argument for a deliverable, which will be available in the next quarter. And also we have already identified some first applications. So this is to show you how the real-time monitor, which was developed by the Imperial College of London and it's used by LCG and EGE, has been also kindly adapted to the EUMEDGrid community. So you can see the sites in Italy, Greece, and Morocco, which are already up and running. So this is a very good start. And this is the view that you have of this pilot infrastructure with grid eyes, which shows you the number of run jobs, etc. So this is a very good start for the project. We have already some information to show on the web, and this is witnessing the good willing of all the partners to speed up this work as much as possible. Now, this is one example of applications which can be deployed on this grid. This is a groundwater modeling applications which aim to estimate essentially the water in the ground, and so to find out how we can sustainably extract it and improve the way of using it. And it's an already EGE supported applications which we are planning to port also on EUMEDGrid. And this is one of the outcome of this application, a simulated map of water levels. This, we think, it's of good importance for the region. So, next events in EUMEDGrid will be a tutorial in Istanbul, in Turkey, next July. Then we have planned a conference in September in Rome, Italy. You are all invited. And another tutorial will also be attached to it in conjunction with EU-China Grid. And we are planning to have another tutorial before the end of the year in Morocco. So look at the website if you want to be up to date with those events. Now, let's start with the China grid. China grid also started on the 1st of January and has also 24 months duration. And the contribution of European money is a bit less than 1.3 million. The main objectives is to essentially contribute to the creation of human network, promoting the international collaboration between Europe and China. We have also the idea to disseminate the European experience on grids in China and to make a good confront with the Chinese experience. They have their own software. We will support interoperability of EGE with the corresponding Chinese infrastructure. And this will include one particular item, which is IPv6 compatibility. We also are aiming to use the existing network infrastructure and foster eventually its development, as I will show you in a moment. And we will try also to foster the interoperability of solution in different disciplines, which will be available with a broader grid technology uptake. And obviously, we will try also to harmonize European and Chinese e-science users' infrastructure and requirements if possible, and provide recommendations for that. So the participants are 10 partners. Essentially, 6 of them are in the European area, and 4 of them are in China, Beijing. We have particularly significant participation of Chinese institutions like the Computer Network Information Center of Chinese Academy of Science and the School of Computer Science in Beihang University, or the Institute of Energy Physics in Beijing and the Peking University in Beijing. We have a couple of third parties. One is the Academia Sinica in Taiwan, and the other one is the Physics Department of University of Rome 3. So this is the splitting among all the work packages. WP2 will be specifically dedicated to networks and study of interoperability, with particular activity dedicated to IPv6 grid interoperability. And we will also address interoperability of grid middleware between EGE and CCN grid in WP3. WP4 will be dedicated to applications, so EGE applications like LHC experiments, biology, etc., which are already grid enabled. And then we will also try to use a astroparticle experiment activity like ARGO in Yanbeijing, which is dedicated experiment to gamma ray bursts. And finally, we have a specific biology application, which is the so-called never-born proteins, which I will discuss in a minute. And finally, dissemination and advanced knowledge of advanced knowledge grid technology will be of primarily importance. So this is the network we are planning to use. Actually, the communication with China for research activities is going through US and coming back to Europe. This TNC2 will allow us to have direct connection between GEONT and China. It is already a network which is already deployed and is useful already. And there is another project funded by EU and which just started, which is called Orient, which will upgrade the 622 megabits lines of TNC2 to 2.5 gigabits. So will allow us to specifically upgrade the connectivity to China to the gigabit world. So this is a map of the CN grid infrastructure, which covers many scientific centers and research centers in China. And we are working with them to understand how to make this interoperable with EG. The center of the Computing Academy of Science is also the center of management of this infrastructure. So one of the issues which we would like to attack is this compatibility of grid middleware on IPv6. We will make a study, an hands-on study on this issue and try to see on a real situation if the functionalities of grid are really available on IPv6 networks. And this is done because essentially IPv6 is one of the goals of Chinese networks. In this moment, they are implementing and deploying a large production IPv6 network, and this will be probably one of the largest IPv6 network in the world. So it is primarily important to work on this and try to understand if grid services are smoothly working and interoperable with the IPv4 without any difficulty or any issue. I mean, obviously, we don't think this will be the case. There will be work to be done yet. So, this is one of the applications, which is the Argo Yanbaijin laboratory. Yanbaijin is a location on Tibet at 4,300 meters on the sea level. And it's well positioned to look at the particle showers in the atmosphere, and this is important to understand the origin of those particles, like protons, but also gamma rays, which are coming from the universe. So the experiment is planning to take data on the order of 250 terabytes per year, and so we require to have a steady transfer rate, which is quite important, and which has to be distributed in China and in Italy at least, which are the two main countries which are investing in this laboratory. So this is a data grid which is under development. Another interesting application is the so-called never-born proteins. And it's, I mean, groups of biologists that they just look at the possibility of combining the different, the different amino acids, and they found that the possibilities are very large. I mean, of the order of 20 to the 60 if you use 20 different comonomers. Instead, you have in nature of the order of 10 to the 13 to 10 to the 14 different proteins, which are the real natural proteins. So there are basic science questions related to the fact why did nature choose this kind of proteins only, this small set from the huge amount of possibilities that were available. And second question is, do these never-born proteins have specific properties which can be of interest to us? So obviously the experimental trials on these combinations is out of question, because the number is so huge that will take an infinite amount of time. So the idea that they are using now is to use simulation to simulate those proteins and see which are the correct combinations which made good proteins which can fold normally, and try to understand which are the properties of those proteins. And then when they find something which may be interesting, this will be passed to the real experimentation in the laboratory. So this is a huge amount of computing power that is needed, and it's a very interesting application. So the achievement in the first 4 months of China Grid is that we had a successful kickoff meetings with very good attendance. We have already done a first tutorial for users and site managers in Beijing, which also was attended by more than 40 Chinese persons. And this will be the core of Chinese trainers in the future events in China. We have also preliminary pilot infrastructure which has been set up with 6 sites, and first application requirement analysis which has been started. So you have here the same real-time monitor that you saw before, but applied to China Grid, thanks to the Imperial College of London, which helped us in doing this. And you have the view with the great eyes of those 6 sites which are already running sites. So we have 2 sites in China and 4 in Europe. The next events, there is a coming workshop in China from the 12th to the 13th of June, which you are all also invited to attend if you wish. There will be interesting arguments like grid on IPv6 and things like that. And there will be a tutorial which will follow. Then we have scheduled another tutorial in September in Rome, and a conference in Rome in September as well, and you are also invited to that. So, conclusions are, is that the China Grid and UMed Grid are both you-funded projects, and they are aiming to promote the extension of and the interoperation of grids infrastructure outside Europe. They will exploit the existing networks which are co-funded by Europe, and we think we have done already good activity in the first 4 months, and obviously we think that we have both in both projects have already achieved important results, creating the human network which of scientists which are enthusiastically participating to those projects. So thank you very much for your attention.
So thank you, Federico, for these nice overviews. The floor is now open for comments or questions. Okay, if not, let's thank again the speaker.
Thank you.
And we move on to the second presentation. As I said, the two final presentations will be on more technical issues. The first speaker is Miron Livni, and he's a very well-known person in US and the rest of the world for grid computing, and he will talk us about data placement in Open Science Grid.
Okay, good morning. Let me just move it here a little bit. Thank you. So if anyone promised you that I will give you solutions today, then that was a misrepresentation, because tell you more about what we don't know how to do than what we do know how to do. So I would like to do two things, talk a little bit about data placement and then talk about, interleaved about data placement and Open Science Grid. So since we are at the networking conference, so I would like to bring up something that I wrote many years ago that basically says that networks allowed us to create communities. And I think it's important that we don't think about what we are dealing with as systems, getting too much excited about latency hiding and sophisticated flow control algorithms, but to basically ask the question, why do we come together and what brings us together? And, you know, when we deal with these kind of things, it's probably good to take a little bit of a historical perspective. But before that, let me make sort of a statement that you may throw me out of here right away. We are spending a lot of time dealing with allocation of bandwidth, and I'll claim that bandwidth is not the issue. We have more than enough. And I think part of the reason why you brought all of us, the users, over here, is basically to help you to do something with all this bandwidth that is buried all over. So I know that networking people don't like to hear it because they want even more and more bandwidth. But what I would like to tell you today is that the problem is not the resources, the problem is what we do with it. So in order to take a look at it, let's start with a little bit of historical perspective. So here's what Philip Enslow said and published in '78 in Computer. Basically saying, here are all the wonderful things that distributed computing can do. These are the benefits. This is what's so wonderful about it. And I'm sure that you will find a lot of similarities between this list and all the recent claims for advantages and benefits that recent technologies, including grids, promise to deliver. And whenever you see something that was known in '78 and we still promise to deliver it, you should ask yourself the question, how comes that we didn't do it in the last 30 or 35 years? And the answer is, that, as always, it's not easy. It's very hard. And again, the problem is not the resources, it's not the flops that we had then versus the flops that we have today, or that the networks then were too slow to do what we want to do. I think the problem from the beginning until today is that we don't know how to manage these systems in a way that will actually deliver to us all these wonderful things. Now, why should we be interested in it? And you heard in the previous presentation, there are a lot of scientific applications that can benefit from it. And what is the real value that we can bring to science? I would argue that there are three. One is which is very close to my heart, and it's dealing with democratization of computing. Namely, that if we can do distributed computing right, we can bring a lot of computing power to and when I say bring, not only to tell them here it is, but to make it accessible to them in terms of ease of use, to scientists all over. And this basically, I like to summarize by saying you don't have to be a super person in order to do supercomputing. The second one is that if you have access to this capacity, you can do speculative science, and I think that this is extremely important in order to move forward, and I think we see more and more of it. And the third one is actually what I'm going to focus on today is really the technical side, which is the data shipping versus the function shipping. Once again, a problem that we have been facing for the last 30 years. The database people are still arguing when is it the right thing to ship the data and when is the right thing to ship the data, the function. But if we do distributed computing right, then we have the option. We can ship it or we can ship it. What it is different. And what I'm going to talk to you today is really about the problem of what does it mean to ship data, or what does it mean to place data. But since I brought in science, let me quickly give you a little bit of an overview of the Open Science Grid, as the organizers asked me to talk a little bit about the Open Science Grid. So the Open Science Grid is a national high-throughput distributed facility that we are putting together in the United States. And it's different than some of the grids that you heard about, is because it's really coming together from a bottom-up approach, where the different partners are coming together in order to do more science. And what sort of symbolizes it is that it is a consortium. It's not a project, and actually it came together before it was even funded. And it is motivated by the stakeholders. If the stakeholders are successful, are happy, then we have an open science grid. If they walk away, then we have a closed science grid. And as you can see here, once you get into a consortium, you're getting into some interesting management structures, that you have a council, and you have an executive board, and you have an executive team, and you have an elected executive director. And anyone who wants to hear more about it, I'll be happy to tell you more about it later. But that is what really is coming together. And you see we have here the experiments and the software provider all coming together and saying, okay, how can we work together in a way that benefits all of us? So once again, it is not that we are getting our funding through it. What we are getting funding for is to create what we call the facility, which is the core of the Open Science Grid. And what we are also doing there, which is important to us, is to focus on local, campus, regional grids as the building blocks. So I'm very proud that finally we have a Fermi grid, because I've been arguing to, for example, my colleagues at CERN, how comes that they are such big believer in grids, but they don't have a CERN grid. They don't manage their own resources as a grid. So anyone who is interested in hearing how Fermi has been struggling on creating their facility into a grid, it's a good exercise on figuring out what does it mean to run a grid across the resource that you have inside your facility before you go out and you gridify the world. So here are the sites, and the point is that it's not only US. Because of the experiments that are working with us, we are obviously bringing in things from South America, Taiwan, and Korea. And we didn't have to remove any letters in order to make it an international effort, like other names. And going back to networks, this is just ESNet. You see, there's a lot of stuff out there that interconnects all this. And I don't even understand what all the colors mean. But all I want to tell you is that there's a lot of it, and there's Evelyn, and there's Internet too, and there's this. And the question is, what are we going to do with it? So, can we do function shipping? Can we do data shipping? And maybe the simplest thing to think about at the moment is we want to ship an object. And when I speak about an object, this is not the objectivity object, which is a very complex thing. I'm talking about an object which is just an array of bytes. And, recently there are manufacturers out there that are strong believer in object store and say, if we can do down below just placement of object. So let's think about object. I have a string of bytes I want to move from one place to the other. It's not a file, it doesn't have a name, it doesn't have metadata. Let's keep it simple, just move it around. The problem is that I would argue that we don't know how to do it. If we have any kind of a handle on how to do CPU management, when it comes to data, we are at loss. And part of it is that we don't even have any kind of a smooth model to deal with data from the byte level to the petabyte. It's all a bunch of kludges that we are going up and down, and we are moving it. And the problem of data is, again, not new, because we always had small, fast memory and slow, big memory. And we always had to ask the question, how do we put stuff here and how do we put stuff there? And the British started doing it already in '60 by virtual memory, and the problem hasn't changed. But we don't have even a way to deal with it. And the first thing that we decided to do is to introduce the notion of a data placement as a job. It's not a side effect. It's not something that you're doing some ugly script that's running in the background and suddenly move the data. Moving data is a first-class citizen. It has to be treated like this. And then as you go down the list here, is, for example, you need to have a smooth transition of CPU and I/O interleaving, because if you have to wait, what do you do? If it's there, how do you respond? All these old problems, but again, at different scale, not only at the byte level or at the page level, but also at the terabyte level. Because I think that one of the interesting things that we are going to see now is storage is becoming so cheap that everyone is going to have huge amount of storage. And people would like to simply put the data that they need on the storage, which means that we have to have a lot of tool. I mean, we need good tool to do effective management of data movement. So here's what a scientist really wants to do. A scientist wants to take X, apply to it F, call it Y, and put it at L. They don't want to think about anything more sophisticated than that. That's all they do. And in order to do this in a distributed environment, here's sort of a very simplistic plan that I will argue we don't have the mechanism to do it. Let's forget policies. Let's forget about when should I move it, how fast should I move it. I need just a mechanism. I need a mechanism to allocate space for the input and the output and the transformation. I need a mechanism to figure out how much space I need for the output. One of the biggest problems that we are facing today in managing any of our grids is the disks are filling up and suddenly the whole thing falls apart. Very basic. Allocate the space. Select the place where you want the data from to place it there. Select the place to execute it. Then execute it, the easy part. Then take the stuff and ship it back. And then clean up the mess. Garbage collection is one of the hardest problems that we are facing, not only as a society, but in any of these systems. We can generate garbage much faster than we know how to collect it. So this is simple. And yes, people will start telling me you can do it in parallel, you can interleave it. What do you want to do first? Do you want to get the data first, the CPU first? I know all that. But give me this, and I'll be happy. So what we have been trying to do is to take a very simplistic approach and say, okay, we'll take a directed acyclic graph as the way to implement these plans. But we will treat the data placement and the execution as first-class citizens. And actually, if you look out there and you see what people do, for example, the Atlas experiment, they are building more and more decoupled systems. One is dealing with data and the other one is dealing with execution. And then when the data is there, the execution happens. Much looser coupling than anything we have seen earlier. But again, moving the data is a task that has to be managed. So in order to implement it, what we decided to do is we decided to say, okay, we need a scheduler that knows how to manage data placement jobs. Yes, it has a lot of similarities with CPU, but it's still a different bird if you want to. And that's what Stork is. And I'm going to move quickly because I have only 10 minutes and I want to say, to cover all the different aspects. I hope to hang around in spite of my back after the talk, so if people are interested in more details, we can talk about it. So here's the big picture. Somewhere up there is a planner, and the planner decided I want to do something that includes data placement and execution, sort of creating a DAG. And basically it goes to some kind of a scheduler and say, here's a DAG that I want to run. Here's my workflow. And the workflow includes both data placement and execution. And then, while connecting to the planner for lazy planning or just-in-time planning, it sends down the jobs to Stork and actually can create a matchmaker there that allows Stork, through this arc, to decide who of all these different tools that are out there. And there are many. And I think that trying to standardize them will never happen. So we need somebody that knows how to talk to all of them, because they are there and they hold data and we have to deal with them. But the question is, when can we talk to them? And that's what I will talk about in the 10 minutes that are left. And once this is in place, then I can go to the CPU part, get also planning decisions, and pick where I want to go, and then run my job. and use some kind of a mechanism to access the data. And there are a lot of tools. Parrot is what we have, XIO, RefIO. People have developed a lot of libraries that say, okay, from the application to wherever the data is, we are going to read the file. So this is sort of the big picture, if you want to. But let's take even the simpler part of it. Let's start with not, I'm trying to execute anything. All I want to do at the moment is to say, take Y, which is at S, and put it at L. Tell the system to do it, and I'm going home, and I will get a notification. Think about it, that you're coming to this conference, and you want to have here your 5 terabytes so you can work locally before going. And the conference will give you, I don't know what, half a petabyte of storage so you can work on it while you're attending. I mean, this is today, in terms of cost, getting peanuts. So what's involved in it? So I have to allocate the size of Y at L. Because if I want to write it somewhere, I have to make sure that I have where to put it. So I need help from L. But then, and here I'm getting into the main issue, I need resources on the endpoints to do the transfer. So the networking guys did all this wonderful work, put all this fiber, and put a lot of light into it, and I can move a lot of stuff. But in order to move it, I need the endpoints to participate. And if the endpoints don't participate, nothing goes through. So I need at S resources, I need at L resources, and then I have to bring L and S together. And what's interesting here, that in order to do a simple transfer, I need 2 or more to participate. And I know that we can throw in away, right away, people will say, what about the network bandwidth, and how are you going to pick the network bandwidth? Okay, fine. I don't think that's the problem that we see on the field. What we see in the field is that we cannot control the endpoint. And we cannot decide when things should happen. And as we know, in our social life, is you need 2 to tango. And the question is, how do you get 2 to tango? Who approaches who? Do you come and grab somebody to dance, or do you politely ask to dance? All these things are very relevant to what we are trying to do here. So here's the simple case, where one partner is asking politely in advance whether he or she can dance with the other partner. So there's no forceful dancing. So once again, and those of you who know me know that everything in the world looks to me like a matchmaking problem. But we have a matchmaking problem here, right? We need to find 2 who are willing to dance. So how does it work? There is a matchmaker, and I say, I am L, and I have what it takes to place a file. And I go to the matchmaker. And S comes in and says, I'm S, and I'm looking for an L because I want to place a file there. Right? Because I know that I was told to put L there, and I go to the matchmaker. And the matchmaker says, aha, this is a match, and notifies both parties, you can dance. And then there's always the question of the protocol, even if you know who is the one that initiated. So here we come in and we, let's assume, use grid FTP. I come and establish a control channel, and I say, I'm ready to send something to you. And then I actually do the transfer. We don't have this. I know that it doesn't sound like science fiction, but the thing is that today you cannot do it. So here's something that we did together with the Grid FTP team in Argonne as a supercomputing O5 proof of concept. So the idea is that supercomputing provided a storage cloud with a lot of storage in it, and we have entry points which were a grid FTP server that were positioned in different locations. Each of them had local control of how much they want to dance. They want to dance a lot, they don't want to dance, and this can change all the time. And we have here a set of sources that also were ready to send data into the cloud, but each of them had also a parameter that controlled how many streams they're willing to push in at any given time. So what we did is we put a stalk, which is a scheduler, next to every data source, and we created a matchmaker where these guys were sending out information and saying, this is how many connections I have that can be used. And then we used matchmaking and claiming to map the jobs from here over here. Stalk controlled how many outgoing connections, and through the matchmaking, we controlled how many ingoing connections can go. And I don't have the numbers now, but we could manage thousands of transfers this way. And each side was able to dynamically control how much they want to dance at any given time. By the way, you can take the same thing and map it into what we call a master-worker model, where rather than doing it as a job parallel, you're doing it as a task parallel. You basically create workers, which are GridFTP servers, that establish connections. And then the work is the list of objects that you want to move. And then you feed them to these workers and get things transferred. So you have finer granularity in terms of when you move things in and out. But what's happening, and you're going out there to the dance floor, and people don't ask you, they just come and grab you to dance. You need to protect yourself, right? The problem that today we don't have any protection, for example, on GridFTP, in terms of how many connections, who can access, and what's happening with the storage. So that's another joint effort between my group and the GridFTP people, is to attach to a GridFTP server what we call a nest, which is managing the resources, storage and connection. So you can come to say, I'm a user, I want a lot to park my data, I want to place a file in a lot, and I want to terminate a lot. So some of these basic management aspects of storage that can be used then to participate in a more friendly kind of dancing exercise. And the way that it works is that using the DSI interface that is provided by GridFTP, which is extremely useful, we can basically monitor the activity that are coming in and act on them, authorize them, terminate them according to policies that we have here. And we can even be the one that put the data in to the storage to control the amount of data that's being written. So we have what we call a chirp protocol that allows us to talk to Nest and to invoke the different commands. And once this has been established, then the user can come in with a standard GridFTP call. But whether the connection will be allowed, and whether the transfer of the file will be allowed, and whether this amount of transfer will be allowed, is all controlled by Nest, while the protocol that's being seen by the user is the GridFTP server. So if you want to turn an existing transfer to a more civilized transfer, where you ask permission before you do anything, like you should, then you can wrap it around the GridFTP server call, get the permission, and then clean up. So what I would like to do here is leave you with this kind of challenge that I think we all face, is we have, I would argue, unbounded amount of capacity out there. Because for every gigabyte or terabyte transfer that you can give me, I can add another one with very little cost. So the capacity is unbounded. I'm also positive that once we will give the community easy tools to do data placement, they will use it. And they will put in their offices terabytes of storage, which are extremely cheap today, and will say, I want the data here. I don't want to depend on anything when I need to access the data. So just place it here, and then place something else, if it is dependable. If it is something that you just hit the return button and say, this terabyte tomorrow morning is on my desk, and you go home, and you don't worry all night whether it will actually make it. So the same thing that we have with computing, because we have the same problem in computing. But I think we are much more advanced with computing than with data. And what we are also missing is that we don't have any way today to cleanly, systematically interact, control the movement of the data and the computing. It is still a very different world. Now, people will come to me and say, what about this, what about this? I would argue that a lot of these are point solution, and we don't have a clean model that deals with everything, including faults, including space allocation, including matchmaking between sender and receiver to make it all work. Thank you.
Thank you, Maren, for this presentation. Are there questions or comments? Yes. Coming.
I just have one quick question. You had mentioned the matchmaking problem of finding someone who can provide data and someone who can then store data there. Mm-hmm. How do you see, or let's say, where do you see the technology in the perspective of comparing it to kind of like email as being an unsolicited file transfer mechanism? I mean, a lot of people use that because it's extremely convenient and they don't have to ask before they send. Right. I mean, the worst thing they get is an error if it doesn't go through, and it's okay.
But this is pretty bad. Yeah. So right. If space is unlimited, then you don't have a problem. But it happened to you, I assume, many times that you send a big file and it came back and it didn't tell you even what the error was, whether the mailbox is full. You see, the point is that you have to find a way to deal with these errors is one. And the other one is that you need to find a way to control what you are allowing to come in. Okay? So, I mean, this is sort of another talk which is dealing with the whole issue of circuit breakers in a system. So, it's fine for you to be forceful. It's fine for you to come and say, take it, and I'll deal with it. But what you have to make sure is that the other side has the ability to say, take a hike. I don't want to talk to you. I don't know who you are. And the thing is that when you're dealing with email, you have humans involved. And you see an error, and you take an action, and you call on the phone. Here we want a system that works. And I think we need more than that.
Yes, Miran. I think there is a fundamental difference between CPU and disk, is that essentially you can share CPU resources, but it's very difficult to share disk resources. And the problem comes from the fact that normally, I mean, you can force out the program when it ends and then the CPU is still available for somebody else, but it's very difficult to, to make people use to delete their files when they are not more useful for them, and this makes the disk resource things which is really abundant, because you cannot predict how many bytes people will use, and the more you give them, the more they use it, because it's there. What do you think? It's
so I think we need to have quotas. First of all, there is a difference between transient data and permanent data, and I've been more dealing with transient data. By the way, when you have to do a context switch, it becomes an I/O problem, by the way, because you have to get everything out to disk and back, and you have to make sure that you have the disk to store all the image. So we don't have today tools, even on a single machine, to allocate storage space to a user. I mean, the only thing that we have is a quota system. But it's very crude, and it's not guaranteed even, because you can oversubscribe and a lot of things. You cannot come and give somebody an allocated space. I think that the first thing that we have to do is to start managing space in a better way. And then we'll have to change some of the culture. But I agree with you, the data is different. But I can move away data. If data was produced, I can reproduce it. I think there is a lot of flexibility if we have a reliable, dependable system to manage the data, rather than saying, oh, I lost the data, I don't know what it is, I don't know who it belongs to, I'm screwed. But data is different. I mean, no doubt about that.
I'm Aaron.
Now comes the network.
No, not at all. This time not. What do you think, taking it one level higher, what virtual machines and virtual machine technology will mean for this? Because then you can get just the next layer of encapsulation, abstraction, and so on.
Yes. So I think that virtual machines are going to help, but I don't think that they're solving the fundamental problem. Because when I invoke a virtual machine, I still have to give it space. And I have to enforce it across virtual machines. And I have to decide how much you get. And then there's always the question of how do I move what we call the sand into the virtual machine and out of it. So I think that there are advantages there, but I don't see how they fundamentally change the problem.
Well, you can assign one application to one VM, and if the VM has fixed,
Right.
disk space allocated with a file, then you know at least that this kind of application problem is solved. But also abstraction of all the things away.
Right. So in terms of sandboxing and allocating space, you're right. They still we have to know how much space to allocate to it, and we have to deal with what do we do when we need to expand it, to shrink it. It helps, but I don't think that it does solve the problem completely. But we can talk more about it.
Okay.
I was waiting for it.
Okay, thank you very much again, Moran. And we move on to the last presentation of the session. Jennifer Scott from Argonne National Lab and the Globus team will talk us about monitoring and discovering in a web services framework the functionality and performance of MDS of Globus Toolkit 4.
Right. So I'm in probably the worst possible speaker slot of the meeting. I come after Maroon Lipney, who's always extremely dynamic, and right before lunch. So I'm going to be talking on a narrower scope than something like Condor or data transfer. I'm actually going to be talking about a grid monitoring system. And this is actually a nice progression because, as Maroon said, compute has always been a first-class citizen. Data transfer should be as well. However, once you have compute and data, you really want to know, well, what's going on with these things? In order to have a more reliable and dependable system, as Maroon just said, we need to have better monitoring and better understanding of what's happening. And so I'm going to be talking about the monitoring system that's part of the current GT4 release. It's a web service-based system using all the standard WSRF standards that are out there for the interfaces and such. And I'm going to walk through, I'm going to give a couple definitions just because everyone has their own and I like to share mine to make sure we're on the same page. I'm going to walk through the basic functionality. Then I'm going to tell you about a couple deployments, one with TerraGrid, one with Earth Systems Grid. So this is my standard opening slide for every single talk I give these days because everyone defines grids a different way. My definition, and in a monitoring space, this really is going to make a difference. I'm talking about resource sharing, where resources are just about anything. And you want to monitor all of these different things, compute, sensors, storage, networks. It could even be people. You've got coordinated problem solving. So it's not one person on a single machine with a single application. It's multiple people in multiple places working in a coordinated way. The way this is reflected in a grid monitoring system is you don't want to advertise out data that's only of interest to one person or one project or one site. Grid monitoring systems are meant to advertise out data that's of interest to many people at many places. We've also got dynamic multi-institutional virtual organizations. What does this mean? This is basically community overlays on the classic structures. You've got multiple people with different roles, perhaps. In this virtual organization, you've got shifting resources and people that you've got to keep track of. Grids are made harder by this lack of central control, the shared resources, and the increased need for communication. It's not an easy problem, but we do it because we have to. The applications we're looking at have shared data by definition, so they've got to use multiple sites. They've got compute needs that are more than a single site can handle because of deadlines. So, for example, it doesn't do you any good to predict the weather for tomorrow if it takes you 3 days to do it. So what do I mean by grid monitoring? I really mean sharing community data between sites. Data is of interest to more than one site and more than one person. Often we're using summary data to help scalability. Most of these systems use an XML-like format. We do as well. This adds on overhead, unfortunately. Really good for some things, really bad for other things. So, for example, for cluster data, instead of advertising out low-level details for each of your nodes, you want to be able to summarize that to homogeneous subclusters as appropriate for your system. We've got to be able to deal with failures. Both the information sources and the servers will fail. If you've got a hierarchical approach, which most of these monitoring and grid systems do, we've got to be able to withstand failures at many levels. And the data is likely to be inaccurate. Marone and I have argued many an evening over how predictions are dreadful and how that's just not the right way to do it because your prediction is always going to be wrong. I'll say up front, any monitoring system is going to give you data that is inaccurate. It will do the best that it can, and usually that's pretty good. But by the time you get the data, it's out of date. It doesn't matter what system you have. In a grid environment, often getting, say, Q data from the last 5 minutes, it's as good as getting Q data from the last 2 seconds. Probably if it's older, if it's an hour old, for example, that's not going to do as good. So a lot of thought has to go into what kind of data you're collecting and what kind of accuracy that you need and what kind of update rates you need. Because, of course, you've got this flex between how often you get the data and the weight on your servers. The other difference is, from a lot of the other monitoring talks you'll probably hear at this meeting, we're looking at end-to-end monitoring. We're not looking at low-level network monitoring like iPerf or another one of these very fine-grained systems. We're really looking at end-to-end performance monitoring. This is generally user-level data. Most of the data that we advertise out can be seen by anyone. It is not secure data. It is not admin-only data. It is data that also can be gathered by user-level tools for the most part. The data can be static and dynamic, and it's generally coarse-grained, as I've mentioned. Okay. So those are kind of my definitions. Let me walk you through what we actually do here. MDS4 is a grid-level monitoring system. The primary use cases are resource selection and error notification. Resource selection, a user has a job or some data that they want to transfer, and they're trying to decide, where should I get my data from? Where should I run my job? Where's the best place to put my effort into? It's part of the Globus Toolkit version 4, which has been out there for just over a year now. And it uses many of the standards that GT4 is involved in, primarily the WS resource properties, base notification, and service group. What this gives us is a standard way to do subscription for data, notification when data changes, ways of describing your data, and ways of grouping it in order to make it easier to handle. It functions as an hourglass to provide a simple interface to a number of different tools. So in the grid world, what you're really doing is dealing with heterogeneity. All of your different sites might have different cluster monitoring systems. They might be running different sets of services. They might have different queuing systems. But a user would like to have a single way to do queries against this data. They don't want to remember, okay, for PBS, in order to get the number of nodes, it's minus n. For ganglia, it might be minus p. They just want to have a single interface, and that's what we give them using these WS standard interfaces and standard schemas where we can, especially the glue schema. MDS4 has 3 basic levels of components. We have information providers, which are the basic information sources. These can be any web service. In fact, all GT4 services have a little bit of data built into them, and a wide variety of non-web services, which I'll go into in a sec. We have some higher level services. We're primarily using an index service, which is a registry with caching, and a trigger service, which is error notification. These are built on top of a common framework. Then we have a set of clients, both Java, C, command line, and GUI interfaces. All of our tools are schema agnostic. All you need to do is pass around a valid XML document. However, we use common schemas wherever we can in order to have interoperability. If I call my operating system OS as a tag, and you call it OPSYS, and someone else calls it operating system, because computers aren't smart, they're not going to understand that we all mean the same component. That's the only reason to have a common schema. So our basic information providers, these are the data sources for the higher level services. We have built into all GT4 services is a little bit of data. This is part of the WSRF standard. What it says is give me a service start time, a version, and a type name. This isn't a lot of data, but it's enough to debug what's going on where. If you don't know these three basic things, you're really up a creek. Most of our services also publish a fair amount of additional data. Thought I had listed here, obviously not. So for example, RFT will tell you, the Reliable File Transfer Service will tell you how many connections it has open, how many ports it has open, how many bytes it's been transferring, how many files it still has to go, etc. Graham will tell you how many jobs it's got running underneath it and some more information. Job-specific data is only available to the person who submitted the job. It's not available more widely. We also have a wide variety of other information sources. An information provider can be basically any executable you'd like. So we've got interfaces to a variety of cluster systems, as I mentioned, and a variety of queuing systems. We can do file scraping. So as part of our work with TerraGrid, they wanted to have some non-programmatic data, names of system administrators, downtimes, etc., which we just scrape out of files. We're also interfacing to other data stores. So for example, we're working on an interface to the standard NetLogger archive so that you can get application-specific data from your NetLogger archive in a generic way. Also, more detailed networking data. This is how we would interface to something like the Pinger archives, would be to give that summary data from an archive. All you need to do is produce a valid XML document, and you can use it in our system. We've got interfaces to Hawkeye, Ganglia, Clumon, and Nagios for basic cluster data. This is all of the stuff that you'd expect to see about what the resources look like, but we can do it in a subcluster conglomeration. So we have a configuration file where the sysadmin defines what are the subclusters on the machines. We dynamically gather information from one of them, a representative node, and say, here's what a subcluster looks like. Most of the groups that we've worked with have organized their clusters this way, and this saves a lot of data, and it's actually what a user wants to see. They don't want to go through a list of 1,000 nodes to find 20 that have the right memory. They want to know, are there 20 nodes free with the memory I need? We interface to PBS, Twerk, and LSF to give you your basic queuing data. This is everything from how long are your queues to what are your policies. This data, these different information providers, then feed into some higher level services. As I mentioned, we've got an index service, which is a caching registry, a trigger service, which does warnings on error conditions. We're currently working on an archive service. These are all built on a common framework, though, which we call the aggregator framework. What this does is it's a piece of software that has these standard ways of subscribing to information providers, a middle piece where you can plug in what the action you want is, and then present standard interfaces, exposing them so it looks like a standard web service to anybody who's out there. Where this do some action for an index service, it would be list the different things, cache the last value. For a trigger service, it's matching. For an archive, it's chuck it into this database over here. This gives us a common configuration mechanism so we can define what data to get, when, how often it should be updated. It gives us a way to do self-cleaning. So if your information provider dies, if there's a way that this is automatically cleaned up, this is very, very useful because we do have failures. We have a soft consistency model, so that means that data isn't guaranteed to be the latest. This is needed in our systems, again, because networks go down, machines go down. And this is all schema neutral. So we only need to pass around valid XML documents. The index service is really the backbone of our monitoring system. It's both a registry and a cache. Like any other registry or UDDI, it maps a data type to the data provider information. So for example, it can say, if you want disk data at this site, here's where you need to query it. However, we also put the last value in our registry and cache it because we looked at our queries and 95% of them were, what's the last value? And this improves our performance significantly. We did a performance comparison of Hawkeye, MDS2, and RGMA at one point in time. And Hawkeye does this actively. They actually actively push their data up. We do it passively. When something gets out of date, we then refetch it into our cache. RGMA doesn't do caching at all and had a tremendous performance. That was the largest difference between the three systems in terms of performance. We have an in-memory default approach. This means at some point we're going to run into a problem because the container memory is what's our limiting factor there. However, we're not even 1/10 of the way there on our largest installation. We're looking at having a database backend for very large installs. You can set up an index service for a specific site, for a set of sites, for a project. So generally, for example, what TerraGrid has done is each site has a local index to that site. Those then register to an area-wide, so they have an East Coast index and a West Coast index, and then those register to the TerraGrid central index. These can all be replicated and duplicated. You can have, so it's a multi-rooted hierarchy. You can also set up indexes. For example, we're working with the Earth Systems Grid. They're only interested in a very small portion of those services. So the services that they're interested in register to a separate index that's only used by their project, just to make things more simple for them. There is no global universal index anywhere. That's in part because nobody's part of every VO. So you don't have any need for something like that. The other high-level service that we've been using for about a year and a half now in production, about a year before that in pre-production, is a trigger service. We actually base this on the Hawkeye work from Condor. What this does is it subscribes to a set of information providers and does matching on conditions. So for example, you can set it up to find out how big your disk is, how much free space is on your disk, and when this reaches a threshold, it'll send a piece of email to your system administrator. Or it can update a web page. It's been used quite a bit for troubleshooting right now. We've got a set of interfaces. The nicest one is the WebMDS user interface. This is a GUI interface based on XSLT transforms, so you can basically take the data and transform it for your project. This is the standard view, which is kind of ugly. I'll show you a better one when I walk through TerraGrid in a second. So these are our different resource types and their IDs. This is a little bit of information about those resource types. If you click on the detail button over there, you'll get additional details. So for example, I've clicked on an RFT. Here it tells me the polling interval, the resource property names, how many bytes have been transferred, the factory start time, how many transfers it's done, how many bytes it's done, and such. And I can click on those as well and get additional detail. This is all doing standard queries. So it's doing what a normal user would do in terms of query. It's just formatting it to make it a little bit more clear to your average user. Okay. I'm going to talk about our two deployments now. I'm trying to do this a little bit quick because I know we're running a bit behind. So we've been working with TerraGrid for about a year now. TerraGrid's a large US project spread across 9 different sites, very heterogeneous under the covers, a lot of different hardware, queuing systems. There's no one mandating you must run this particular monitoring software, you must run this particular queuing system. They're starting to look at what kind of scheduling system to run over these 9 different sites. Unlike EDG, they're not sure which one is the best fit. They've got 4 contenders here that they're looking at. I've actually been told there's another one that's on the books. All of these are going to be gathering up a common set of data to make their scheduling decisions. So the MDS team was approached to deploy a common set of scheduling data for these different scheduling systems. So even though they might have 4 different schedulers running on TerraGrid, they'd only have one source of data. So we've provided them with a set of software that collects this cluster data that I've mentioned at the subcluster level. We can also list per host details, and we list some TerraGrid-specific details for each node. They've got special nodes that are tagged in different ways for experimentation or specific projects. We've got these interfaces to Ganglia, Hawkeye, Clumon, and Nagios, so they're collecting up all of their queuing data, their cluster monitoring data that way. They've got a few homegrown monitoring systems as well. So what we've done is we've provided them a way that if their monitoring system can propagate a set of data in a predefined format to an HTML file, doesn't have to be readable by anyone but us, we can scrape that file and push it out as if it were coming from any of the ones that we've written a standard interface for. This has allowed us a lot of extensibility and a lot more flexibility, so we've been able to give these guys a standard way that any monitoring system that they've grown at home can then be propagated. We also collect the base and queuing data and some TerraGrid-specific attributes. This is the GUI that they've set up. This is the same data, roughly, that I showed you in the other one, but in their particular format with their particular formatting around it. If you actually scroll up, it's got their logos and such on the top. This is just dropped right into their formats. The queuing information is across the top where they've got a name, a unique ID, a version. Then they've got some gram data, the version, the host it's running on, and the port. They've got some information about their local resource management type. one of the interesting things we found out about this was there's no way to tell if you're running PBS, Torque, OpenPBS programmatically. There's no way to query the systems to find out which one you've got. So that's actually some static data mixed in with the dynamic data of how many CPUs we have free, how many jobs we're running, etc. Here's our subcluster data where they've defined these different subclusters, and then the actual host data is shown on the bottom here. So this has been up and running since November in a test system. TeraGrid's in the process of deploying this right now. They've got 7 of their sites reporting queuing data as of this morning when I looked on the website. They're still getting the cluster data up and running. We've got all of this with a fair bit of extension to what was available in the 4.0 distribution, but we've just released a patch. I think it's going to get announced later this afternoon. We've been arguing about who has to actually do the announcement. The other project we've been working with quite closely has been the Earth Systems Grid. What they wanted to do was something rather different from what TeraGrid was looking at. They had a problem where they had users that were on their distributed systems 24/7. They did not have sysadmin support 24/7. And so it was often the case where a user would run into a problem on their systems, and then it would have to get chased down, and what they wanted to have happen was the system administrators notified ahead of time, hey, it looks like something's not going right here, so it could get fixed before the users ran into it. They had a set of services they were interested in particular, and so we've set them up with information providers that do queries against these on regular intervals, and then use the trigger service to match what values are achieved. So, for example, it checks, are things up? Are they performing the way they should? Are you getting the response times you expect? And if you're not only does email get sent to a sysadmin, but it updates this little web page with their smiley faces, and you can actually click on one of these guys, and it will tell you information about the boxes that don't have the smiley faces in them. This was their layout, not mine. They've been using this for almost 2 years now in alpha form and beta form. Most recently, they used it to chase down a file descriptor bug. They were running out of file descriptors. And so we set them up with a little script that would check how many file descriptors you had available. And every time they got close to running out, it would send a piece of mail so someone could then log in and figure out, okay, what application is running that's causing this leak. So it was a really nice, just kind of happened way of debugging it. But really essential, as Maroon had said, to having more reliable services and more trustworthy services underneath things. So I wanted to do a small plug. Globus has just opened up its development environment. Globus has always been an open source environment. It's always had the spirit of allowing outside contributions. We know we can't build it on our own. However, it's been very hard to do that. Very recently, we moved to a more open environment called dev.globus or globdev, which allows outside contributions in a much more straightforward way, not only to existing projects such as the MDS, but if you want to contribute to a new project as well. This is up and online right now. If you go to dev.globus.org, you can get some more information about what projects are there and how to contribute. If we're currently wearing my MDS hat, we're looking for new information providers, new higher level services, anyone who's got an interest in GUI, and even use cases from people. Wearing my incubator chair hat, if you have a project you'd like to contribute, by all means, get in touch with me. As I think I've implied, this isn't work in isolation. I have a great team of developers. Even though I live in Edinburgh, they're scattered between Chicago and California. Here's some additional information. This is me. This is where you can find MDS online. We've got a nice publication that we've got the basic architecture and some performance numbers as well that I didn't have time to chat about today, showing some of the scalability and reliability of our system. And with that, I'll just take any questions. Thank you.
Thank you very much, Jennifer. Other questions or comments?
Lunch?
Okay, if not, let's thank the speaker and all the speakers of the session. So the session is now closed, and enjoy your lunch.